Hello and welcome to my video presentation answering question 4 of the assigned topics. I'll be discussing ideal v van der Waals gases, finishing off by plotting a Maxwell-Boltzmann distribution curve. So let's look at the first question. A sample of neon gas with a mass of 255 grams occupies 3 decimeters cubed at 122 Kelvin. Using the ideal gas law, calculate the pressure of the gas. So first off, let's have a little look at what defines an ideal gas. So when a gas is treated to have no volume, no attraction or repulsion to other molecules, and only perfectly elastic collisions, it's defined as an ideal gas. The ideal gas law dictates that pressure multiplied by volume is equal to the moles of gas multiplied by gas constant multiplied by the temperature. So, before we can input the values given to us in the ideal gas law equation, we need to rearrange it for pressure. The moles of gas, gas constant, and temperature are divided by the volume, isolating the pressure on the left-hand side of the equation. So we can now outline which values equate to which letter in the equation. The volume used is 3 decimeters cubed, the moles of gas is 12.637 due to the division of the mass, 255 grams, by the molecular mass, 20.179 grams per mole. The gas constant used here is 0.08206, with the temperature being 122 Kelvin. So, let's implement the values into the rearranged ideal gas equation. The moles of gas multiplied by the gas constant multiplied by the temperature, all divided by the volume, equates to 12.63 times 0.08206 times 122, all divided by 3. This is equal to 42.17, meaning the pressure of neon gas is 42.17 atmospheres. Part B of the question asks us how the pressure of the gas changes if it's treated as a van der Waals gas. So, a van der Waals gas takes into account the attraction and repulsion of the molecules, the volume taken up by the molecules, and the likelihood of inelastic collisions. The van der Waals equation shows that pressure plus moles over volume squared times the constant A times the volume minus moles times the constant B is equal to the moles times the gas constant times temperature. In this equation, we've been given that A is equal to 0.205, where B is equal to 1.67 times 10 to the power of minus 2. We need to rearrange the van der Waals equation before we can obtain the pressure. nRT is divided by the volume minus the moles of gas times constant B, yielding pressure plus moles over volume squared times constant A. This is equal to nRT over volume minus moles times constant B. Moles over volume squared times constant A is subtracted from both sides of the equation, isolating pressure on the left-hand side. This gives the final equation: pressure is equal to nRT divided by volume minus moles times constant B, all minus moles over volume squared times constant A. We now need to input the values into the rearranged van der Waals equation. So, pressure is equal to 12.369 times 0.08206 times 122, all divided by 3, minus 12.6369 times 1.67 times 10 to the power of minus 2, all of this minus 12.6369 over 3, multiplied by 0.205, with squaring everything after the minus sign. So the first part of this equation is equal to 45.36, and the second part is equal to 3.67. Therefore, when treated like a van der Waals gas, the pressure is 41.72 atmospheres. Comparing this to the pressure of neon when treated as an ideal gas, there is a 0.42 atmospheres difference. So, the second question asks us to calculate the pressure of helium when 40 grams is added to the container without a change in the pressure or the temperature. So to start with, we need to calculate the moles of helium gas. Moles is calculated by dividing the mass, which is 40 grams, by the molecular mass, which is 4 grams per mole. Therefore, 10 moles of helium is present in the system. Next, we need to calculate the mole fraction of helium by dividing the moles of helium by the total moles of helium and neon. Therefore, we divide 10 by 22.6369, meaning the mole fraction of helium is 0.4418. Now we've calculated the mole fraction of helium. To calculate the pressure of helium in the system, the mole fraction is multiplied by the pressure of the system. Therefore, 0.4418 is multiplied by 42.17. This equals 18.63 atmospheres, so the pressure of the helium in the system is 18.63 atmospheres. The third question asks us to find the root mean square of both helium and neon. We'll start with neon using the equation the square root of 3 times the gas constant times the temperature over the molar mass in kilograms per mole. Calculating the molar mass of neon involves dividing the mass of neon in kilograms, 0.255, by the moles present, 12.6369. This equals 0.0202 kilograms per mole, so plugging this into the equation, we get the square root of 3 times 8.314 times 122 divided by 0.0202. This is equal to 388.12, so the root mean square of neon is equal to 388.12 meters per second. So we can now move on to helium using the same equation. The square root of 3 times the gas constant times the temperature all over the molar mass. So the molar mass of helium is equal to the mass in kilograms, which is 0.04, divided by the amount of moles present, which is 10. So the molar mass is 0.004 kilograms per mole. Plugging this value into the equation, we get the square root of 3 times 8.314 times 122 all over 0.004. This equals 872.2. So the root mean square of helium is 872.2 meters per second. The last part of the question asked us to sketch a Maxwell-Boltzmann distribution curve. To do this, we need the root mean square that we calculated in the last two slides, and the average speed of the molecules of the two gases, which we'll work out here. The equation for the average speed involves the square root of 8 times the gas constant times the temperature over pi times the molar mass. So first, let's plug in the values for neon. So the square root of 8 times 8.314 times 122 over pi times 0.0202. This is equal to 357.59, so the average speed of a molecule of neon is 357.59 meters per second. So next, let's plug in the values for helium. So the square root of 8 times 8.314 times 122 over pi times 0.004. This is equal to 803.57, so the average speed of a molecule of helium is 803.57 meters per second. The sketching of the two Maxwell-Boltzmann distributions involves incorporating the root mean square value and the average velocity of the two gases. The difference between the root mean square and the average velocity for neon is 30 meters per second, with a smaller difference and smaller original values than helium. Helium has a larger difference between its root mean square and average velocity, which is 69 meters per second. The values of average velocity and root mean square are also much larger than neon, due to having less molecules, allowing the present molecules to reach a high velocity before having a collision. Thank you for listening to my presentation. I hope everything I've said has made sense, and goodbye.